Hello everyone and welcome to chapter 3. In this video I'm going to be focusing on the term mole as well as a brief overview of mass percent. And so the first thing I have to kind of discuss here is we have words that represent numbers, and you've all come across these at least one point in your lives. I mean, if you tell somebody that you have a dozen eggs, then that person normally is under the assumption that you have 12 eggs. If you say, hey, I need a pair of shoes, and again, normally that person will assume the fact that you need 2 shoes. And so the chemists, we actually have our own special word that represents a very, very, very important number. And that word is mole. And so the mole represents 6.022 times 10 to the 23 anythings. And by anythings, I mean I do not care what the thing is. If you have a mole of particles, you have 6.022 times 10 to the 23 particles. You have a mole of atoms, you have 6.022 times 10 to the 23 atoms. If you have a mole of puppies, you have 6.022 times 10 to the 23 puppies. It does not matter. You have to remember that this word is just a replacement for a really big number. The same way that if you say a dozen, dozen is replaced with 12. Same concept here. You just need to understand that this is an awesome number because it is a great conversion that almost every single other unit has some ties to. And so when we kind of talk about this, when we have donuts or shoes, we can use a dozen or a pair. That's pretty much appropriate for the situation. But whenever we start talking about atoms, or when we start talking about electrons, you have to remember, and again, I'm quoting this from what I've heard years and years ago, there is literally more atoms inside of a piece of sand than there are sand on the entire beaches all over the world. And so in these cases, when we talk about atoms, we are talking about a whole buttload of atoms. And so we would really rather not say, and again, I'm not going to try to tell you this number, but this is a mole. And so rather not say that number repeatedly over and over again. And so Avogadro's number, and again, Avogadro will kind of show up every once in a while throughout the semester, but Avogadro's number just represents the number of things inside a mole. So Avogadro's number is that 6.022 times 10 to the 23. And so one thing you have to understand about this, well, first off, commit that number to memory. And if you don't want to memorize all of it, just remember 6.02 times 10 to the 23. It'll get you in the ballpark most of the time. And so this number is nothing more than a conversion. And so just like we focused in previous videos, whenever I give you equality, or something like 1 mole equals 6.02 times 10 to the 23 things, you now have a conversion between moles and things, or moles of electrons and number of electrons, or moles of atoms and number of atoms, or moles of whatevers into number of whatevers. And so in this situation, this number allows us to actually count atoms without actually having to count every individual atom, but we know some type of relationship between mass and moles. And so when we kind of look at these relationships here, moles is always going to be your middle man. And as you'll realize throughout the rest of this semester, there is always some type of connection or some type of conversion that involves moles in whatever unit you're dealing with. Right now I'm showing you that there's a conversion between mass and moles if you have the molar mass. And again, I just use this little squiggly M just because I don't want to write out molar mass every single time. There's also a conversion between moles and things. And so atoms, molecules, particles, protons, electrons, it doesn't matter. If you know Avogadro's number, you know there's 6.022 times 10 to the 23 things per mole, or 1 mole contains 6.022 times 10 to the 23 things. Either way, you know the relationship is always going to be the same because it's always going to be Avogadro's number. And so one thing you have to kind of take into account here is just set up dimensional analysis appropriately, and everything else should kind of fall into place. One other thing is moles are also going to be related to a lot of other units we're going to come across. So here I'm showing you moles and atoms, but you can also have a conversion between moles and temperature, or moles and pressure, or moles and liquid, and moles and volume. It's all going to come back to moles. So become very, very, very comfortable with using Avogadro's number. But if you're not yet, here's your practice. So, how many grams of silver are in 0.0342 moles of silver? And I give you the molar mass of silver is 107.9 grams per mole. And so if you're given a molar mass right off the bat, you have a conversion handy. Especially because I'm telling you the units here are in grams per mole. It should be a huge indication that this is a conversion between, you guessed it, grams and moles. And so first thing you need to do with these types of problems is figure out what information are you given, what unit are you starting off in, and then figure out what unit do you want to end up in. If you have a direct conversion, then you're done. You just need to plug it into your calculator. If you don't have a direct conversion, then again, just kind of take it one step at a time. Figure out what conversion you do have, see what you can cancel out, and then go from there. So first thing here that we're looking at is we are going to convert from moles to mass. And as I mentioned, because I give you the molar mass here in terms of grams per mole, we have a conversion between moles and mass. And so the next thing you need to do is just make sure you have everything set up appropriately. And so here, because we started off in the units of moles, we want to make sure that we put moles in the bottom of our conversion. So here we want to set it up as 0.0342 moles of silver times 107.9 grams of silver over moles of silver. In this case, we can just double check, and I promise you, still to this day, when I'm working these things out on paper, I still make sure to draw these lines. Because if you do not mark out your units, the one time you don't do it is whenever you're going to be taking an exam, and it's going to cost you some points that you don't want to get rid of. And so in this case, just make sure your units cancel out. Your moles of silver cancel out moles of silver. The last unit you're left over with is in grams of silver, which luckily is what we are looking for. So let's flip things around. How many gallium atoms are in 2.85 times 10 to the negative 3 moles of gallium? So same kind of idea here. We are starting off in one unit and we want to completely change that unit. And so you have to ask yourself, what are we starting at and where do we want to end up at? And so here I'm telling you that I want to convert my moles into atoms. And so if you kind of notice here, I didn't give you a molar mass. The reason for that is because I don't care about mass. I'm not asking anything in terms of grams or anything like that. So molar mass wouldn't do you any bit of good. But one unit, conversion that you need to have memorized is Avogadro's number. And so Avogadro's number states that there are 6.022 times 10 to the 23 anythings. In this case, the anything that we happen to be looking at is atoms. So I'm telling you there are 6.022 times 10 to the 23 atoms in 1 mole of one mole of gallium. And so when we kind of go through and look at this is our conversion. This is what we're looking at to get from atoms to moles. So just set it up appropriately because we have moles given to us. We want to make sure that moles is going to be on the bottom to cancel everything out. Here we have the setup, so moles will cancel with moles. And we're left with 1.72 times 10 to the 21 gallium atoms. So please note, this is a big number. That is a lot of atoms, and that is pretty much the typical amount of atoms in a very, very small amount of moles. So one more thing before we can move on to the next video here is we have to kind of figure out how to tie all this stuff up together. And so in the previous 2 slides, I mentioned or showed you how to go from mass to moles, and we also discussed how to go from moles to atoms. And now if you can follow along with me here, I set this up in a particular way because you can tie those two calculations together. And so say that I want to kind of go all the way, and I want to go from grams all the way to molecules now. And so not just grams to moles and not just moles to molecules, but kind of do a double conversion here. So the first thing we're going to start off with is what we are given. We are given 22.5 grams of CO2. And so as I mentioned several times with these types of problems, even if you have no idea what the heck you're doing right now, just make sure that you find some conversion that contains what you are trying to get rid of. And this time we're trying to get rid of grams of CO2, So find some conversion that might be handy or even like written right there in front of you that will get you from grams to something else. And so the only thing I've actually mentioned in this problem is 44.01 grams per mole. And so using that conversion, make sure that you put grams on the bottom and moles just happen to be on top. So your grams will cancel out with grams, and now we're sitting at moles. And again, typically if you are given moles of something and you seem to be at a dead end, Avogadro's number is usually the best bet to kind of go through because you're talking about moles of things. And so here we're asking to convert your moles into molecules. And so it doesn't matter what those things are, molecules, atoms, pickles, doesn't matter. As long as you have a mole, you know there's going to be 6.022 times 10 to the 23. In this case, those things just happen to be molecules. And so set it up with your CO2 molecules over your moles of CO2. Moles cancel out moles. Your final answer is going to be in terms of molecules. And so this next slide, it doesn't look too scary. I just want to kind of bring it up that this schematic is going to show up many times. It's just going to keep getting bigger and bigger. And so as I kind of stated earlier, moles is always going to be your middleman. If you have no idea what the heck you're doing and if you're stuck in a problem, convert it into moles. That's usually always going to be the first step. And so here again, I'm showing you the same thing I kind of showed you before. If you want to go from mass to moles, you're going to use molar mass, which is given to you in grams per mole. If you want to go from moles to things, atoms, molecules, electrons, protons, whatever, you're going to use Avogadro's number, or 6.022 times 10 to the 23 things per mole. Now, one additional idea here is if you are given a chemical formula, then you can use that chemical formula, and it also has a relationship to moles. And so when we kind of go through and take a look at all these things here, so in this example, if we look at how many formula units are in 41.6 grams of ammonium carbonate, or I give you this fancy chemical formula here, which again, if this were an exam question, you would not see that chemical formula, so be sure that you know your nomenclature from my previous videos if you haven't looked at them yet. And so, one thing I have to point out about this particular question is I call these things formula units. The only reason why I'm calling them formula units and not molecules is because if you take a look at ammonium carbonate, we are looking at an ionic compound. And as I mentioned in my chapter 2 videos, we refer to these things, or only molecules, in terms of covalent bonds. And so these cannot be called molecules, and so the easiest word they have is formula units. And so basically all I'm really saying is how many of these entire pieces or these entire things are in 41.6 grams of those things. In addition to that, the second part I want to know is how many oxygen atoms are in this sample. So one thing you should kind of like notice here is I don't really give you a molar mass, but I do give you the masses of each of these individual components here. And so I did this just to kind of show you another concept I kind of like skimmed over in the previous chapters, but you need to know how to calculate the atomic or the molecular masses of these things, or formula masses for ionic complexes. So the first thing we need to do is get some type of beginning point, or the molar mass of this compound. The way we do that is, again, figure out how many of each of these atoms there are inside of this complex and substitute those masses in for those numbers. And so one thing you need to pay attention to is subscripts. Every single time you see subscripts, you're either going to get very efficient at them, or you're just going to keep ignoring them. It's going to really make you angry. And so in this situation, we have NH4 2, so that 2 needs to be distributed out to the nitrogen and to those 4 hydrogen. So we actually have 2 nitrogen, 8 hydrogen, and then this one, 1 carbon and 3 oxygen. And so if we kind of look at these, how it's calculated, 2 times the molar mass of nitrogen, which I give you as 14.01, plus 8 times the molar mass of hydrogen, or 1.01, plus the molar mass of 1 carbon, or 12.01, and 3 times the molar mass of oxygen of 16.00. If you didn't catch all that, here it is in all its glory. And so in this case, you come out with a 96.11 grams per mole for your ammonium carbonate. And this grams per mole, as in the previous slide, should kind of give you an indication now that you have a conversion between mass and moles. So, start with part A. And so I want to know how many formula units are in 41.6 grams of ammonium carbonate. And as I stated before, if you even have no idea what you're looking for, just take it one step at a time. And then another hint is moles are always going to be your middleman. So if you're stuck somewhere and you have some type of conversion that will get you from whatever you're looking at to moles, just do it. And even if it's not part of the problem, do it anyway. It's good to get into the practice. And so starting off with our mass in terms of our molar mass, we know we can convert our mass to moles using our molar mass of our NH4,2CO3. And using the concept that this whole entire video is over, or Avogadro's number, we know we can go from moles of this NH4,2CO3 to the number of these formula units. And so just using this scheme that, again, it's not new, it's the same scheme from the other previous slides here. But here we have 41.6 grams of our NH4,2CO3, and then use the molar mass, making sure that the grams are on bottom so grams and grams can cancel out. The next step, just make sure you put moles on the bottom so your moles and moles can cancel out. And just to be on the safe side, draw some lines through these units just to make sure you're actually telling the truth to yourself. Once that is all well and done, plug into your calculator, and you have 2.61 times 10 to the 23 formula units. And so, this is going to be a very, very, very common calculation throughout this entire semester. Converting masses into moles, or volume into moles, or pressure into moles, and then doing one additional step to convert your moles into whatever your unit you're actually looking at is going to be at least 75% of the calculations you're going to be doing. And so again, I know it seems kind of cumbersome, but you need to be very, very efficient at this, especially when it comes to your timed quizzes or timed exams. If you can't do this very quickly, then you're going to run out of time in most of your assignments. And so part B, you guys all forgot there's a part B, right? So part B asks how many oxygen atoms are in this sample. And so once we know the number of formula units, which we just saw for in part A here, I tell you that there is 2.61 times 10 to the 23 formula units. And so go back and recall what I called or what I meant by formula units. And all I'm really saying here is that there's 2.61 times 10 to the 23 NH4,2CO3s. And so great thing about this chemical formula here is it tells you the relationship between each of the constituent atoms or each of the pieces of this formula unit in the entire thing. By that I mean this chemical formula of NH4,2CO3 has 3 oxygens in it. So we know for each one of these entire complexes, you are going to have 3 oxygens. Or again, if we know that we are going to have the number of our formula units, we multiply that by a very convenient number that has been mentioned a couple times, like 3, then we have the number of oxygen atoms. And so in this case, all I'm doing is, that's a 3 there, so you know there's 3 oxygens per one of these. We just calculated that we have 2.61 times 10 to the 23 of these, and so each one of those contains 3 oxygens, or 3 oxygen atoms per each one of the formula units. Make sure formula units cancels out with formula units, and we're left over with oxygen atoms. And so what I'm really trying to show you here is dimensional analysis is going to have a lot of pieces. It's going to have a lot of steps associated with it. But you cannot get overly frustrated with it. You just have to take a deep breath and take it one step at a time. I promise you, with practice, this will become second nature to you. You might not like it, but it will become second nature to you. So the last piece of this first video of Chapter 3 is going to be discussing this mass percent. And so we kind of touched on mass percent a little bit in Chapter 2, but I gave you the percent and you had to figure out the chemical formula or the empirical formula from that. Whereas in this situation, I'm telling you how to solve for the actual mass percent. And so one thing I have to kind of point out is you are all familiar with how to do this already. Basically, whenever you take an exam, you are looking at the number of questions that you got correct out of the total number of questions. And once you figure that out, you have the mass percent, or you have the percent that you made on the grade, or sorry, on the exam. And so in these cases, if you're looking at the mass percent of a sample or of the element out of a sample, you just need to take the mass of that element inside the sample over the total mass. And so this can kind of be a little bit misconceiving whenever you're looking at chemical formulas. For example, as I'm showing on this slide here, sodium chloride. Sodium chloride has one sodium and one chlorine. And so if you just assume that all atoms were created equal, you would assume that the mass of this is going to be 50% sodium and 50% chlorine. But the issue is the fact that sodium and chlorine both have completely different masses. So therefore, sodium and chlorine, unless they're mixed like as a 50-50%, their 1-to-1 atomic ratio does not mean anything about the mass. One thing you need to make perfectly clear now before we start moving on to further ideas here is mass is completely different than atomic ratio. Mass ratio, atomic ratio, not the same thing. And so if we take a look at this example here, and I want to know the mass percent of chlorine in this C2CO4F2. And so the great thing about mass percent is it doesn't even matter the sample size. It could be 200 grams, it can be a microgram, it can be 3,000 tons. As long as you have the actual chemical formula, the percent is not going to change because the chemical formula can't change. So once you figure out the percent of chlorine in the C2CO4F2, it's going to be the same percent in every single sample of C2CO4F2. And if it's not the same percent, then again, it violates the few laws we talked about in Chapter 2. And so in this molecule, you can see that there are 4 chlorines for every one C2CO4F2. And I know that because there's a 4 next to the chlorine. That's just what that represents. And so since we know that there's going to be 4 chlorines for every one of our molecules, if we want to know the mass percent of the chlorine, we just need to take the mass of 4 chlorines and put it over the mass of our entire molecule. And so first we need to figure out the mass of our entire molecule. And so I give you the atomic masses of carbon, chlorine, and fluorine, so you just need to make sure to plug those in where they need to go. And so here we know that we have 2 carbons, 4 chlorines, and 2 of our fluorines. So plug it in as 2 times your 12.01 plus 4 times the 35.45 plus 2 times your 19. We end up with a molar mass of 203.8 grams per mole. So if we want to know the mass percent of our chlorine, we just need to take, as I stated earlier, the mass of 4 chlorines, or 35.45 times 4, over the mass of the entire complex, or the 203.8 we just determined, and then tie it off into a nice little bow with a 100% sign.